Hello everyone. It's 9:26 p.m. Wednesday, July 2nd. We're gonna continue on with Word Ladder. Yesterday we got partly through, and then I gave up. I threw the towel. I was so tired yesterday, and I was pretty defeated. I'm not gonna lie. We're gonna try again, but this time I'm just gonna actually jump right into the video.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve word ladder. This is a hard problem, but I don't think it's super difficult. There's just one little thing that kind of makes it really annoying to get this to pass on LeetCode. But the idea is we're given a beginning word, and we're given an end word, and we're given a list of words. We want to create a sequence from this beginning word to the end word, and the end word is definitely going to need to be a part of our word list, but the beginning word actually might not be a part of the word list. And so we want to create a sequence from the beginning word to the end word. That sounds pretty easy, but there's one restriction that we have to follow, and that restriction mainly is that every adjacent pair of words in that sequence can only differ by a single character, exactly one character. They have to differ by exactly one character. And so we want to find a sequence from that beginning word to the end word where every word in between is a part of the word list, and we want to return the shortest sequence. So the sequence will basically be the number of words. So for example, in this example down here, we can see there's a sequence from the starting word hit, and notice how this is the beginning word, so it doesn't have to be a part of our list of words, but every other word in the sequence does have to be a part of the list of words. And that includes the end word, so cog does have to be a part of our list of words. And so in this example, the shortest sequence is of length 5 because it has 5 different words in it. Now, the convenient thing for us is that every single word, including the beginning, end word, and every word in the list is going to be guaranteed to be the exact same length. In this case, every word has 3 characters in it. So it's pretty easy to take 2 words and figure out what's the difference in characters between them, right? We can just compare character by character and see that there's 1 character difference. Therefore, we could form a path between these 2 words, right? And each edge between these words, let's say log and cog, is going to be bidirectional, right? We could go from log to cog, or we could go the other direction, right? So this is starting to look like a bit of a graph problem, right? We want to find the shortest path from the beginning node hit all the way to the end node cog, and the way the edges are going to work. So hit could be connected to any of the words in this word list where it has a single character difference. So let's think about this. So hit, which one of these words could it be connected to? Is there a single character difference between hit and hot? Yes, that's the case. So hit and hot are going to be connected in this problem. What about dot? Nope, it takes 2 character difference between hit. What about dog? Again, 2 character difference. Lot, again, 2 character difference. Same with log and same with cog. But hot could be connected to some of these characters or some of these words, right? So we're realizing that building a graph like this with all the edges, like an adjacency list pretty much between the words, is going to be very helpful for us. And there's a naive way to create this adjacency list, which is going to basically be a nested loop on the entire list of words, which let's say ends up being n squared, where n is the number of words. And let's say the length of each word, which is always going to be the same, is m, because we're going to need to compare character by character between the words. So creating that adjacency list is going to be something like n squared times m. But, and you might think that that's good enough. Unfortunately, this won't pass on LeetCode, and I really think that's kind of stupid that it does that. The main thing to notice to build the adjacency list faster is to look at the constraints. They tell us that the length of the list of words, in our case that's n, so it's going to be n squared, right, is going to be less than or equal to 5,000, whereas the length of the word itself is going to be less than or equal to 10. So there's actually a way where we can change this time complexity to at least generate that adjacency list to something like n times m squared, because the m is going to be smaller than the n, so we can actually make it kind of like this. But I'm pretty sure that the overall time complexity, because after we actually create this graph, we're going to run a breadth first search algorithm to find the shortest path. We could do it with DFS, but usually to find the shortest path, breadth first search is much more efficient. And I'm pretty sure, even in this case, the breadth first search solution is going to be n squared, because this is going to be the number of edges we could potentially have, right? Because that's how many words we have. We can have n squared edges, and we're also going to have to compare words. So on each operation when we're traversing the graph, it's going to be multiplied by the length of the word. So the overall time complexity for the BFS is still going to be n squared, which is, pretty much this. So you might think, well, then why isn't it passing on LeetCode? And that's a good question. I think in general, though, doing it like this is going to be faster. We use this to generate our adjacency list, and then we do a BFS with this time complexity. And basically, there's kind of a small trick that I'm going to show you, which will get it to pass on LeetCode. So like I said, the first part is building an adjacency list, and the naive way would be to go through every word hot, compare it with every other word. That's going to be n squared, and then the length of the word, which is m. But there's a little bit of a trick. So how about we do it a different way, right? We know that for any word, we want at most 1 character difference, right? So let's take a look at hot, our first word, and let's take a look at every pattern it could fall into if we change 1 character at most. If we change the first character to any other character, we could transform this into star for the wild card, and then ot, right? We change the first character. We could also transform it into h, change the middle character, star, and then t, right? And then also to a third word, ho, and the last character is going to be a star, right? So these are the 3 patterns that hot fits into. And now let's take a look at a different word, dot. And let's quickly do the same thing for this. So the first pattern will be star ot, next d star t, lastly d o star. So notice how, okay, these 2 patterns between the words are different. These 2 patterns between the words are different, but the first pattern for each word is the exact same. Since these both of these words, hot and dot, have the same pattern, when we remove the first character, that means that they have a 1 character difference between these words. And that makes sense, right? If we change the first character from here to a d, or change the first character from here to an h, these 2 words will be the same. That means they have a 1 character difference. So using this idea, we are going to create an adjacency list where the key of the adjacency list is going to be the pattern. By pattern, I mean one of these wildcard type strings, and the value of this adjacency. List. In our case, it's going to be a hash map or a dictionary. So each pattern is going to be mapped to a list of words. So each pattern to a list of words. So for example, if we take the pattern star ot, we'll have a corresponding list of words for all words that fit this pattern, right? So far we found hot fits this pattern. We also found that dot fits this pattern. And by just looking at our list, we can see that lot is also going to fit this pattern. So we have 3 words that fit this pattern. So if we wanted all the neighbors of hot in our adjacency list, how would we find them, right? Because the key, it's not like hot is the key of this adjacency list. So to find all the neighbors of hot, what we have to do is first for hot, find all of its patterns, right? The first pattern, star ot, will go to that star and say, okay, these are all the neighbors of hot. These are all the neighbors. in the graph, of course, we can't include itself, so we'd say, okay, dot and lot are going to be the neighbors of hot. But we also know that hot can have a couple other patterns that it fits into. H star T. Are there any other words in our list that match this pattern? Well, hit is going to match that, right? Hit is going to match the pattern H star T. So in that list, we would have hot and hit. So that's how we get another neighbor for hot. And lastly, we'd see, are there any other words that fit this pattern HO star? In our list, you can tell that I don't think any other words are going to fit that pattern. Only hot itself fits that pattern, so it doesn't have any additional neighbors. So all the neighbors of hot are going to be dot, lot, and hit from up above here. And so
Interesting. Interesting. This problem is I don't like this problem. The fact that we have to kind of do this like janky adjacency matrix thing is kind of not cool. But he did say that's the only bad part of the problem, so I guess after that it's not that big of a deal. I don't. I'm not gonna lie. I don't like this at all. I'm kind of tired of doing these graph problems. Actually, I'm extremely tired of doing these graph problems. I'll keep it a buck. Oops. Damn it. Do it again. Oops, I did it again. Alright, Okay, so I have this. This is not really an adjacency matrix, though. Curious, like, what the
So how are we finding the neighbors? So basically, what's the computation of what I just did? It's going to be, since to find all the neighbors, we're going to have to go from hot, consider, okay, if we remove this character, remove this character, remove this character. So basically, we're going through every word in our list, which is n, and then we're going through every single character that we remove, which is m, right? So that's how many possible different patterns we could have in total. And then to actually add each word to the list is going to be another m. So that's kind of how you can get the complexity n times m squared to at least generate the adjacency list. Now let's assume we have that adjacency list and we have a graph. Then the algorithm is actually pretty...
Wait. What?
You can get the complexity n times m squared to at least generate the adjacency list. Now let's assume we have that adjacency list and we have a graph. Then the algorithm is actually pretty straightforward. It's just going to be a basic BFS search. So this is something like how our graph is going to look like. We know that the beginning word is hit, the destination word, the end word is cog. So we want to find the shortest path from here all the way to here. So we know that a good way to find a shortest path is a BFS search. So from our first initial spot, we're going to look at all neighbors that it has. From the picture, it's pretty obvious. Hot is the only neighbor. So far we have a path of length 2 because we're counting the number of words. That is what determines the length of the path. And of course, it's not going to be this simple to get the neighbors because we know that our adjacency list is a little bit more complicated. And again, from hot, we're going to go to its 2 neighbors, and we're never going to revisit the same neighbor twice, but we are going to potentially have to go along each edge at least once. We're also not going to go along the same edge twice, but the number of edges I'm pretty sure could be the number of words n squared. And for each neighbor, to find each neighbor, we're going to have to do an m operation where m is the length of a particular word, which is where I'm getting this time complexity n squared times m. I'm pretty sure LeetCode has the wrong time complexity for this. Somebody can correct me if I'm wrong though, because for a graph with n nodes, the maximum number of edges could be n squared. And again, from here, so we don't want to, even though there's an edge between these 2 nodes, we don't want to go along that edge because that's going to be revisiting the same nodes twice. So now we're going to go along our next layer. So from dot, we can reach dog, and from lot, we can reach log. Now there's just one last unvisited node. Both of these log could visit it or dog could visit it, but at the end, we're going to have another node. So what was the path? So we had 1 word, 2 word, 3, 4, 5. It took us 5 layers of our BFS to reach this. So we're going to say that our result is 5. And when you look at the output, that's exactly what they had as well. So with that being said, we can jump into the code now. So now let's get into the code. And like I mentioned, we want to make sure that the end word is actually in the word list because that's a required dictionary. But in this case, it's going to be helpful to do this. Basically, this is a dictionary where if we're inserting a new value for the first time, the default value is going to be an empty list. Also to our word list, I'm going to go ahead and append the beginning word because it's not a part of the word list initially. So begin word. Now let's actually build the adjacency list. So first, let's go through every single word in this word list. And now for each word, we want to find every possible pattern for this word. So I'm going to use a pointer J just to go through every single position of this word. Of course, we know every word is going to be the exact same length. And for each position of this word, I want
okay, wait,
to replace a character with the wildcard character. So I'm going to transform this string word into a pattern string where we're going to take the first j characters. Initially, j is just going to be 0, so we're going to take that. We're going to replace the jth character, the 0th character, with a star, and then we're going to get the remaining characters skipping the jth character, so j plus 1.
I guess I can get rid of the 0, huh?
1 to the end of the string. So we're just going to go through every position, replacing a character with a star, and then for this pattern, we're going to say, okay, in our neighbor list, all the strings that fall into this pattern, so for this pattern, we want to append the current word. We want to say this word is a part of this pattern, and that's going to help us traverse the graph later on. And of course, we're going to do that for every single word in the entire list, and we're going to have that star go in every position of the word. Next, let's do our BFS. There's a couple data structures we're going to need. We don't want to revisit the same position twice, so we're going to have a set.
Really? I'm confused. Where's the adjacency matrix? This is an adjacency matrix. This is gonna have...
Set to make sure we don't do that. We know we're going to start at the
That's the other m adding it? Why? Isn't this O of 1 to do that?
beginning word. So let's add beginning word to the set. And we also need a queue. And we're going to similarly add the beginning word to this queue. And we're just going to continue popping. We're going to go layer by layer until we get to the end word. And initially our result or our length of the...
What's up, bro? How you feeling? Meow. You good boy. Yeah, you good boy. Yeah, you good boy. Alright, that's fine. That's fine. Max, I know, I hear you, brother. Can't be doing all that. Alright, we're gonna do visited equals a hash map. I'm gonna say Q1 equal to begin word, and then Q2 is equal to a blank. I just want to say wall Q1. I wonder how he does BFS. I'm actually curious. I feel like I'm doing it wrong. Okay, so I have to check if the queue is empty. The Q2 is like a circling thing, so like if Q1 empties, Q2 refreshes. So like Q1 will equal Q2, and then Q2 will be refreshed. It'll be flushed down the toilet. Okay, and then we should get to top value and pop it. And then I'm gonna write a note here saying 1 layer deeper. If node is equal to end word, then we return depth. Oh, well, my back hurts. Ah. And then else, if it's not, oh, then I guess we'll say let's say visited node was correct. It's true. And let's say for neighbor and neighbors. So I haven't written out anything for neighbors. If neighbor not, if neighbor not in visited, and Q2 dot append neighbor. Okay, so now I need to create neighbors. Sorry. Let's mess with my arm for a second. Oh, my back is killing me. Oh my god. Oh, yeah, I'm only gonna do this problem because my back is actually frying me right now. And I'm gonna make a thing up here. I'm gonna just call it def get neighbors. I don't like this. I feel like this is trash, but it's whatever. Okay, this is chopped. This is chopped cheese right now. Okay. I think that'll do. Get neighbors of node. And I'll do a depth equals 0. Depth plus equals 1. And a return depth. I have a very strong feeling that this is not going to work at all. Would you look at that? Not really surprised at all. So I return nothing. Just interesting. Print Q1. I want to see. Oh. Sure. Why not? Read that. Split. Oh, you know what? Yeah, sorry. Forgot. Return 0. I'm guessing 50. Oh my god. Thank the Lord. Stupid question. I hated that question. I kept thinking DFS, which is my fault. I should have came to my own conclusion and realized that was BFS, not DFS. But the hard part about that problem is just creating your adjacency list. It's just data management, which is like, I get it, I understand, like that's a problem that you face in the real world, but like not really, you know. I don't know. sorry. I have to take a look at something. Okay. Dynamic programming. It's been a minute. Oh, how I love you. I don't. If I remember correctly, dynamic programming can be easy or it can be stupid hard. So let's see which one we're gonna get today. This is supposed to be an easy, but I remember doing this problem. If I can just remember how I did it, it shouldn't be too bad. So DP involves memoization, which is the process of caching previous solutions, so that way you don't have to reuse them. It also kind of involves a little bit of what we were doing with the graphs, which is like branching out. So that's why it kind of breaks down from backtracking. So it's basically like okay. Hold on. Let me scale draw this. I'm gonna try this out myself first, but I am 1000% watching the video afterwards, even if I do get it right, because I can guarantee you I'm not going to get the correct process. So, let's cure this stanky problem. Let's do that. So here I stand with 0 steps taken. So I can either take 1 or 2. And then here I can go 1 or 2. 1 or 2. Okay? And each of these is its own unique kind of branch. So if our target is like 3, then this is valid and this is valid. So they're both valid. So this is, I'm trying to think should be like a fairly simple problem. I don't know if this one even really needs caching, but like DP is all about caching, so it's like, do I really feel like I should not cache? Because I feel like that might be wrong. Oh, you know what? No. I remember now. The cache will basically be if you have n steps. Sorry, if I have 2 steps, like if I'm at currently like step equals 2, I could check that in the cache. Oh, my back hurts. Goodness. I'm remembering it now. I'm remembering it. Okay. That's not right. I need to truly actually think about my recursive thing. Ah, that's what I hate, man. Gosh. All right. Let's do this way. So this is my base case. This returns 1. So this will be 3 ways, right? Okay. So this will be 5. Is it really that simple? Alright, let's check it. Oh, yeah. No cash. Wrong answer. There you go. Alright, let's watch the video, as I said I would. Because I am curious to see if I was on the right track.
Hey everyone, welcome back, and let's write some more new steps, right? That's what this 5 steps read.
Oh, he does the other way. Turn a Boolean? I mean... Whoa! What? What? Math. Interesting. Oh, that's pretty cool. It's even faster version. Huh. Cool. Alright, my back is killing me. I need to get up. I need to walk around. Thank you for watching, and I'll see you tomorrow.